Hey guys, and welcome to our intro lesson for the mole. Now, the mole is a really fundamental idea to chemistry. We're going to be using moles basically from now until forever that you are doing chemistry stuff. And so we're going to make sure we spend a lot of time here today just getting it down pat and knowing the very basics of it. Now, when I talk about, that's not what I want. I want my pen. When I talk about a mole, I don't mean like the little fuzzy animal that digs holes, right? It's got to mean something else. So let me give you a little history on what this mole is and why we need it. So let's start here. Historically, chemists have really wanted to find some way to count how many particles are in a certain mass of a substance. So let's say I give you a glass of water. You could weigh that. Let's say it weighs 50 grams. How many individual water molecules are in that glass? If you know the exact weight, I want to know how many atoms are there. If I give you 5 grams of sodium, how many sodium atoms do you have? Now that's really important, because in chemistry, you've got that conservation of mass idea, and that comes from conservation of basically atoms. When you're balancing equations, right, you want the same number of atoms on both sides. Well, if you could figure out a way to know how many grams that was, you could actually make the recipe for a reaction. So let's say let's start really easy. Sodium metal plus chlorine gas gives me sodium chloride. All right. Now I got to balance this. I need 2 chlorines, which means I need sodiums. Cool. Okay. If I say this, okay, I want you to mix actual sodium metal with actual chlorine gas to make some salt for me. Well, A, don't do that because it would be a massive explosion. But how would you do it? You wouldn't mix 2 grams with 1 gram. That wouldn't work because the particles have different weights. 2 chlorines is going to be way heavier than a sodium is, so you can't just use grams. You would need to mix 2 atoms of sodium with 1 atom of chlorine, and that's just not, you can't just grab your science tweezers and pull out an individual atom at a time, right? It's not going to happen. So we need a way to convert mass to particles, so I know how many grams I would actually need to make this recipe work. So I would have a perfect reaction with no leftovers. So mass in the periodic table, right here now, mass in the periodic table is always measured in atomic mass units. Now, those units are way too small to be of use in a lab, right? They measure how much a single atom weighs. I don't have a scale. Nobody has a scale that'll measure a single atom. So we can't use those numbers. So chemists decided that the easiest way to count the particles would be to find some constant, some number that relates atomic mass unit to something more measurable. Can I look at, let's say, I'd grab my periodic table, I look at beryllium, and it says the atomic mass unit, 1 beryllium weighs 9.01. Can I convert 9.01 into some kind of number that I could weigh on a scale? Some kind of number of grams, maybe. That would be really handy, right? So they did a ton of work on this, tons of very smart people pounding away. They finally found the number, the constant, some kind of conversion factor between atomic mass units and grams, or number of particles, I guess I should say. They named it Avogadro's number. Now, Avogadro was a very famous scientist, did a lot of good work, and so he got a number named after him. Kind of cool. Real smart guy. Not very pretty, but very smart guy. This is the number of particles that you need for their combined weight to add up to the atomic mass from the periodic table in grams. So if I'm looking at my beryllium example, beryllium is 9.0122. That's its atomic weight. So how many atoms would it take me to get this many grams? So for example, they looked at hydrogen. Hydrogen's atomic mass is 1.008. So they figured out how many particles it would take to get 1.008 grams of hydrogen. And the weird part is 1.008 grams of hydrogen has the exact same number of particles as 9 grams of beryllium. Because beryllium's bigger and heavier, it's the same number of particles. So we know exactly how many atoms we need for something we could measure in grams. So that's kind of it's like a magic code for us in chemistry. It is huge. Once chemists had figured out this number, well, they named the amount of substance 1 mole. So that number of atoms we call a mole. So here's the important part. Circle it, square it, highlight it, underline it. You're going to need this. Avogadro's number, which gives you 1 mole of a substance, is 6.02 times 10 to the power 23 atoms. 6.02 times 10 to the 23. So if I had that 1 gram of hydrogen, or 1.008 grams, it's exactly 6.02 times 10 to the 23 atoms of hydrogen. If I had the 9.0122 grams of beryllium, it's 6.02 times 10 to the power 23 beryllium atoms. Now, moles, it's just a measure of quantity, right? If I have a pair of shoes, I have 2 of them. If I have a dozen eggs, I got 12 of them. If I have a mole of particles, it's 6.02 times 10 to the 23 of them. So it's just a word that represents a number. So if I say I got 4 dozen, I would do 4 times 12. If I've got 4 moles, it's just 4 times this. So now, though, atomic mass on the periodic table becomes a lot more important because it tells us 2 things. It tells us the mass of a single atom in atomic mass units, which is not that handy, but it also tells us the mass in grams of a single mole of atoms, 6.02 times 10 to the 23 atoms. And so if that's the mass of a mole, we call it the molar mass. So I can look at my periodic table and say, hey, what's the molar mass of hydrogen? And you just look it up and say, oh, it's 1.008. So let's try it. What's the molar mass of nitrogen? When I ask that, what I'm actually saying is, how much does 1 mole of nitrogen weigh? How much does 6.02 times 10 to the 23 atoms weigh? And it's easy. You grab a periodic table, you look up nitrogen on it, and you see it's 14.01. Or the periodic table I have tells me 14.007. Same thing, just slightly different accuracy. And it's measured in grams per mole. So every mole of nitrogen weighs 14 grams. All right, that wasn't too bad. What about compounds? What do we put things together? So if I want to find the mass of 1 mole, 6.02 times 10 to the 23 particles of a compound, you just add the molar mass of all of its particles combined. So, okay, carbon monoxide. I look up carbon. It is 12.011. I look up oxygen. Oxygen is 15.999. All right. So how many do I have? I've got 1 carbon atom. I've got 1 oxygen atom. I'm going to round these a little bit just to make the math easier. If you'd like, you can definitely keep more precision. So I've got 12. 1 times 12.011 is basically 12. Plus 1 times 16. So their molar mass of carbon monoxide is approximately 28 grams per mole. I mean, you could do the exact math if you wanted. Let me just pull up my calculator here. Let's find out. So the exact molar mass would be 12.011 plus 15.999. Turns out the exact mass, according to this periodic table, is 28.01 grams per mole. So if I wanted to weigh out a mole of carbon monoxide, I would need to weigh out 21.01 grams. And that is a much more measurable number, right? You could actually weigh that on a scale somewhere. Let's try nitrogen dioxide. Nitrogen weighs 14.007. Oxygen weighs 15.999. Cool. I have 1 oxygen. I have 1 nitrogen. I have 2 oxygens. So I've got 14.007 plus 15.999 times 2, which gives me 31.998. So I just did this math, put that number there, add those together, 14.007, and my molar mass is 46.005 grams per mole. So I would weigh out approximately 46 grams of nitrogen dioxide, and that would get me very close to 1 mole equals. There we go. Now a fun one. The molar mass of magnesium nitrate. All right. So what do I need? I need magnesium. I need nitrogen. And I need oxygen. Okay, so I look up magnesium in my periodic table. Magnesium is 24.305. I look up nitrogen, 14.007. I look up oxygen, 15.999. Okay, now I need to know how many of each. So I look back up here at my chemical formula. I have 1 magnesium. I have how many nitrogens? Well, I got 2 sets of NO3, so that means I have 2 nitrogens and 2 times 3, 6 oxygens. So this will give me 28.014. 6, I'm going to do that one on my calculator. 15.999 times 6, 95.994. And then I just add all of these numbers together to get my total molar mass. 95.994 plus 28.014 plus 24.305 equals. So if I wanted a single mole of magnesium nitrate, I would need 148.313 grams. That is the molar mass of magnesium nitrate. So the bigger your compounds get, and the further down the periodic table you go, the heavier things get. So don't be surprised if big compounds like this are over 100 grams per mole. I mean, if you were to go way down to something like, I don't know, mercury itself would be 200 grams per mole before you even put it in a compound, because mercury is really heavy. It's got a molar mass of 200.59. So that's molar mass. It's going to be very fundamental to the stuff we do in chemistry. So we're going to spend a little bit of time practicing this, working on calculating it so you guys can get really good at it. And then we can move on with what we use it for. So thanks for watching, guys, and I'll catch you next time.